Okay, so today's the first day of our last 2 weeks of this semester. So we will be finishing up chapter 5, and the only thing that's remaining will be the stochastic processes chapter 6, which we will see some Markov chains and steady state probabilities, probabilities that change over time, or states of random variables that change over time. And that will be our last topic. But this week, let's finish chapter 5. And your last assignment, which will be a programming assignment, will be on chapter 5. And I'm going to show you an example, which is very similar to what you will be seeing in your last assignment. Okay, so we have seen up to now, we have seen how to sample from discrete distributions by partitioning the domain into partitions and sampling from them, and using uniform discrete numbers to see which interval that uniform number falls into, and then generate that discrete variable. And also we have seen the inverse transform method, the norm inverse or the exponential inverse, which gives you a way to again use uniform numbers due to the fact that the cumulative distribution function of any random variable, any distribution in any distribution is uniform, standard uniform. So we take the inverse of that standard uniform, the CDF function, and if you feed standard uniform numbers to that, it will give you X random variables which are coming from the original distribution. So the idea was this. For example, so this is the standard uniform for any CDF of X coming from any distribution. Its CDF is, if it's continuous, its CDF is always standard uniform. So you first find the inverse of this, the inverse function for the CDF, and then, which means that if you give U, you're going to get X. So that's what you do. You just sample from standard uniform, you give it as input. So in terms of the MATLAB Octave Online application, it was really easy. We just use norm in. Yeah, that we had this example. Statistics. Okay, so norm in, you sample, the first is the parameter you give to the norm, not the parameter, the input that it gets to this norm inverse function. Then, for example, you want to generate random numbers with mean 18 and standard deviation 5. Okay, so you want to generate normally distributed numbers with mean 18 and standard deviation 5. And this is what you get. The numbers we get here are normally distributed numbers. If you get a lot of these, for example, we can put this in a loop, or we can also get this as an array. Well, I mean, we can just fill it an array and look at the histogram afterwards and see that it's going to be normally distributed. Okay, so and now today we're going to see if when the CDF is difficult, the inverse of the CDF is difficult to compute analytically, and this may be the case for arbitrary continuous distributions. We may not have the inverse function directly. If it's difficult to solve for X, and if the PDF is already available, if somebody gives you the PDF, did not give you the CDF, the PDF is available, it's difficult to inverse the CDF, then there's another alternative methods to sample from continuous distribution. There's methods like importance sampling and rejection sampling, and this rejection sampling method is what we're going to use in this class, what we're going to learn in this class. So let me see, I'm recording, yes. So it can be used to generate random numbers from this PDF, given this PDF. This time we will not be interested in the CDF. We are given a probability density function for a variable X. And the idea is to generate 2D uniform coordinates within some bounding box of this PDF. We are going to bound our PDF in some rectangle. it's the bounding box. And if we are going to generate these two random numbers, which are uniform, which means that we are going to be generating uniformly from this box. If the PDF, okay, so what will happen is that if we plug in the generate x coordinates, so PDF is already available to us, which means that we can just evaluate it at any x. We are going to evaluate it, and we are going to see whether the generated point's y coordinate is below the curve of that PDF or above the curve at that point, at that x. If it's below, it means that this PDF is large at that point, and we output x as the generated sample. So the idea is this, it's in this figure. So if this is the PDF, which looks like Gumbel or distribution or gamma distribution, I'm not sure. So it's skewed. We see that it's a skewed distribution, and this is the probability density function. So we get this bounding box, which is between a and b. X's are between a and b. Okay, and if you have a distribution in which the tails go all the way to infinity, it may be difficult to get a bounding box like this. But even in normal distribution, it gets to very close to zero. For example, 4 standard deviations away from the mean, it will practically be zero. You don't want to generate, okay, it's even with this example with mean 18, standard deviation 5, it is possible to get a value of minus 60. Okay, minus 60 is a possible, but its probability is maybe 1 in quadrillion. I'm not sure. I mean, it's maybe even lower than that. It will be very small probability, which you can ignore. You don't want to generate a minus 60 number with this mean and standard deviation. So what you can do is practically, in practice, you can actually bound, even if it's the tails are going to infinity, you can bound when it reaches very close to zero. You can put a bound there for your x values between a and b. Okay, the other thing is you have to find the maximum point of your probability density function. What is its max? Here, c is used here as the max, but it's not, it need to be exactly equal to the maximum point. Roughly, for example, in this figure, it shows that the value c chosen for the bounding box is actually a little bit above the maximum point of this fx. It will not be too critically important. The idea is, if we generate random points from within this box with the x coordinates between a and b and y coordinates between 0 and c, okay, so we're going to generate two random numbers. One between a and b, uniform random number between a and b. So we can use standard uniform and scale it by multiplying with b minus a and moving it to a so that it starts at a. So it's possible to get a standard uniform random number and make it between a and b. Okay, so it's possible for any standard uniform number, just translating and scaling it. The same with 0 and c. So its bottom is 0 in this case, in this PDF. So all you need to do is scale the second uniform random standard uniform number you generate so that it's between 0 and c. So we have an x coordinate and y coordinate. Let's assume the point is this one, the two uniform numbers we generated. If what we'll do is we're going to plug this x into fx, and what it will give us is this. Let me write it here. So this point here, as you can see, oh, this is not a good color. Let me change this. So look at this point here. This point here is fx. When I give this generated x to this one, it's this point. So I compare in rejection method, basically I compare the heights of y is compared against this one. If y is smaller, what we do is we output this x as a generated random variable. If y is larger, for example, for another point, it will be this. It will be, if this is another xy, this would be that fxx will be this point. In this case, we are not going to. We reject this. Let me change the color. In that case, we reject this x and we don't, so it's rejected. We don't output it as an x. As you can see, in this case, the PDF, the probability of the point probability for this x is smaller than this, or the probability to get a value to output an x within a certain interval here is much lower than the probability to output an x in this interval. So that's basically the idea. It's really intuitive. So you generate points here. All the points that are generated here outside, they will be rejected. The points that are generated here, so this one actually is going to be accepted. Let me move it there. I moved it outside because it was a red point. So the points that are here are going to be accepted, and you can see the points that are accepted are roughly equal to the area under the curve. For example, is the ratio of the points that are accepted is the ratio of the area under the curve over the area of the entire rectangle. Okay, so that's the method. Some questions you may have is, how do we find C? You either plot it or you find the maximum point by taking the derivative of your PDF. You can take the derivative of your PDF and set it to 0 to find its max point, and you can have your upper bound at that point. Or you can just plot it and visualize it. Visually, you can set what the C is going to be. All right. So there is an example in the book, and this is actually a distribution of beta distribution, not Gumbel distribution. It's a beta distribution, and it has two parameters, alpha and beta. This was the distribution for, this specific distribution was alpha 5.5 and beta 3.1. And its a PDF is this. It uses this gamma function, gamma alpha plus beta, divided by gamma alpha times gamma beta, x to the power alpha minus 1, 1 to the minus x to the power beta minus 1. So it's rather a complicated function. And the values are defined between 0 and 1. So A is 0, B is 1. Okay, we know that. It doesn't have actually tails that go off the infinity. It's defined between x, 0 and 1. So what we do is we first find the bounding box. So this is A, B on this figure are named S and T. Those are the bounds for the generated x values. And M here is the C. The highest value it will get for the values of this alpha and this beta is going to be 2.5. So that's our bound for the generated y coordinate. So what we do is this. So this is shown as a capital F here, but actually it's lowercase f. This is the PDF, right? So this is the PDF evaluated. So it may be a little bit confusing. Maybe I should update the slides to show that. Actually, take a note of this. This is not the CDF function as indicated here. This is this fx, which we should also have used while programming, not to confuse ourselves, because the capital F is usually used for cumulative distribution function. So this small f, we evaluate it at this x that we generated. So how do we generate this x? Did we generate it yet? No, x is equal to 0. So we should get a random variable, random number here. So what is going on here? Let's see, this x is 0, y is equal to m. Oh, okay, I see what you're doing. We first generated, is this the, no, this is PDF. So let's see what is going on here. So first it generates a value for 0. Okay, and so we will be generating lots of random variables. So here, as you can see, the thing that is going on here is this is just the initial f value that we generated. so that you make sure maybe to enter this loop, or I mean, this is really an unnecessary code, depending on how many numbers you want to generate. So this actually generates X until it rejects all the samples until one is accepted. So for example, if it will be accepted at 0, it will actually output 0 here. Okay, so Y is equal to M, but we know that the first is going to be rejected anyway. So the first, it generates an initial value before going into this while loop. So what it does is it sets Y to M. So the first point it generates before going into that while loop is actually this point. So it generates this point, which we know that it's above the curve. Okay, so it will be rejected. Therefore, we go into the while loop. Y, which is currently M, is greater than 0. F is going to turn out to be 0 for value of X. So the initial value of this is M greater than 0, so we go into the while loop. So we keep generating two uniform random numbers. And as you can see, X is scaled by the width first, and then it's moved to the starting point S. So now X becomes between S and T. It becomes a uniform variable between S and T. And we just scale Y because the minimum value of Y is going to be 0 anyway, and the width of that interval is M. We scale Y. Y becomes a number between 0 and M. And we reevaluate F at this X, and we keep rejecting the points as they are under the curve. If we get a point above the curve, we keep rejecting the points when they're above the curve. If we find the point below the curve of the PDF, we stop the while loop. In this case, F is going to be below the curve, Y is going to be larger, and we output X. So this is for generating a single variable. We do this multiple times if you want to generate many variables for this. And if you run this code for example, 1,000 times, you run this code 1,000 times and fill an array of 1,000 random variable X's, and you plot the histogram, you get something like this. So it's not perfect, but it still it resembles our PDF very well. If you create more and more samples, so these are sampling errors that we see here, which is okay. Okay, we don't expect to get the exact curve here. For example, probably this was taken for maybe 10,000 samples. There are 200 numbers that are here. I think there are about like 10,000 samples, 10,000 random points that are generated for this one. But yeah, you get the idea. This is the code for some beta distribution. And I'm going to show you in the assignment that I'm going to walk through, I'm going to show you another example which has an arbitrary PDF, a polynomial. Actually, it's a piecewise defined PDF that we are going to see. Okay, so Monte Carlo methods in general basically involve many variables. If we have a problem in which at hand most of the time, which may involve multiple random variables. For example, the time that a uranium atom will hit the boundary steel box, or and in that same thing the time that it will decay, or there may be different times, random variables that are in the system. And it may be not just for a single uranium atom, for example, it may be for thousands of them. Each one of them, or maybe billions of them, and each one has its own, it's a different random variable. So in order to figure out some property of that system, if you want to compute something, what is the probability that all of them are going to decay, for example, in 1 minute? What is that probability? If you want to learn something about these complicated system with lots of random variables, it may be impossible. I mean, not impossible, but it may be very, very, very difficult to solve this analytically. In Monte Carlo methods, we just generate these random variables, simulate a certain sample from that system, and we do it a lot many times and observe, just count in how many of them the favorable case was observed, and just we compute proportions, mean, standard deviations from that sample. And if we have enough of those samples, if the sample size is really large, we approximate the real probability with certain confidence. Okay, so that's basically the general idea behind Monte Carlo methods. Simulate those random variables, simulate it a lot, then count the just compute the proportions from that. And there is actually a part that we have skipped when we were studying chapter 3, which was Chebyshev's inequality. For any distribution, actually Chebyshev has this for, I'm going to come to that. We're just going to be using it as a formula to determine the size of our Monte Carlo study. So there are three things that when we are conducting a Monte Carlo study, we will have two goals at hand. For example, imagine you want to estimate a probability. Okay, for example, you're playing a solitaire game. What is the probability to have a successful solitaire in one deck of cards? Okay, so we're trying to estimate a probability P. What is the probability for for a shuffled deck of cards where you have any permutation of those cards as equally possible? What is the probability to have a successful solitaire game? So we are trying to figure out what this probability P is. Now, in a Monte Carlo study, we will have two goals when we're trying to figure out what this P is. First, what is the precision that you want to attain? How close you want to get to this P? For example, I want to know the actual probability P with 0.01 range. So I want to find a P hat which is going to be, we cannot make this for certain. That will be the other case. That will be the other parameter we will be given. But we will say that I want my desire is to have this P hat within 0.01 of this actual probability. Okay, so that's my desire. And I want this desire to be satisfied with, for example, 0.95 probability. Okay, so these two things, one of them is precision. So this 0.01 here is my precision, how close you want to get to the actual value, and how confident that you will be at the end that you are in this interval. So if you are in this interval with 0.95 probability, so if P hat is in this interval with 0.95 probability, and these concepts are very similar, right? I mean, this looks very much like the confidence interval we have talked about. Okay, so this looks like the margin of the confidence interval, and this is the confidence level, alpha here is 0.05. So with some significance level, 0.05, which means that with 0.95 probability, the generated P hat will be in this interval. So in Monte Carlo simulations, we cannot really have, I want to have 1.0, I want to have 100% confidence. If you want to have 100% confidence, you have to conduct infinitely many Monte Carlo. Your Monte Carlo study size should be infinite. Okay, you always have to make compromises. You will never be 100% certain, and you will never be completely precise. To be exactly, to find the P exactly, in which the margin, if you want to have the margin 0 and your confidence 1.0, you have to, your Monte Carlo study size should be, Monte Carlo size should be infinity. Okay, but we will see that even with very high confidence. For example, you can have with 0.999 confidence. With this confidence and with this margin, I want to find the actual probability within 0.01, and I want to be 0.999 confidence. Okay, these are not exactly 1, this is not exactly 0. We will see that, for example, maybe if you conduct 1 million simulations, your Monte Carlo study size is 1 million, you will be able to attain this. So, but it depends on certain factors, and the Chebyshev's inequality actually relates this margin and this probability for any distribution. That's what, in order to be able to, with these parameters, what do you want for your precision to be, and what do you want your confidence to be? These will be parameters that are given to us, and for that we will have to answer this question: how many Monte Carlo simulations should I run to be able to count these frequencies and compute this p hat? That's our goal. Okay, and we have to determine the size of our Monte Carlo study, and Chebyshev's inequality is going to give us that. So this was from section or subsection 3.3.7. Chebyshev said that it's called Chebyshev's inequality for any distribution with some expectation and variance. So these are any distributions, parameters, expectation and variance. It's not only for normal distribution. Okay, any distribution has an expectation and a variance. And for any positive epsilon, so this epsilon is our precision. The probability that whatever a random variable x, the difference between a random variable x and this x will be your p hat, or whatever you compute after your Monte Carlo study. So the probability to be within the actual mu, the probability within this precision is less than or equal to whatever the variance of your that random variable is. If you divide it by epsilon and take the square, the probability is bounded by this. So in other words, so this was the equation, but we are going to see in examples how we are going to turn it around to find the size of our Monte Carlo study. And for probabilities, for example, we will assume the worst variance. If you're, for example, if you're predicting a probability, the highest variance the probability can get is 0.25, right? Which is 0.5 minus 0.5, which is attained at when p is equal to 0.5. That's the highest variance. So we will be, for example, we will assume the worst variance if we don't know what the sigma is. We don't know what sigma is, we don't know what mu is, that's okay. We will assume the worst. For example, with 0.25 here, with given precision, we will be able to do that. We're going to have a probability here. So for any random variable x from the distribution is within epsilon distance of the mu with probability of at least 1 minus this. So as I said, this was just a side note here. In order to estimate probabilities, how we're going to use this Chebyshev's inequality will be clear in a second. When we try to estimate probabilities in Monte Carlo studies, I mentioned that, for example, if you want to estimate the success probability of a solitaire game, we generate random numbers, or we play random games, solitaire games, and count how many of them were successful in our try. So how accurate is the estimator? And these are our estimate. Standard deviation of p is going to be this. So this is the standard error that we have seen previously. Okay, so here the critical thing is this slide. We are going to be using this slide and saying that all the parameters that I want here are given here. So this is z alpha over 2 is my confidence. For if you want to be 0.95 confident that your probability is within that interval, what you do is, since a Monte Carlo study size is really large, we will be able to also apply central limit theorem. So we will be looking at z tables. So this alpha is 1 minus your confidence, the desired confidence. So you're going to be looking up the z table for a particular confidence level. For example, if you want to be 0.999 confident, alpha in that case is 0.001, You divide it by 2. Alpha 2 is 0.0005. So you find the z-value for this from the table. That becomes, that is put up here. It's going to be a large number. And epsilon, you're going to divide that by your epsilon. What do you want your margin to be? If you want your margin to be 0.001, divide the z-value. For example, z-value may turn out to be 4.5. Okay, this is a really large value. Divide it, for example, with 0.001. It will be, for example, 45,000, right? So yeah, it will be 45,000. Multiply it with 0.25. That will be, you have to have a Monte Carlo simulation with at least that size to guarantee that precision. There's an example in the book, but we may directly jump to our example, homework that I want to show you. But let's quickly go to 5.14 here. Example 5.14 somewhere. It should, yeah, the shared computer. A supercomputer is shared by, and the following problem does not have a simple analytical solution by hand. There's a supercomputer shared by 250 independent subscribers. Each day, each subscriber uses the facility with probability 0.3. The number of tasks. So first, there's the random variable that a subscriber, whether the subscriber is going to use the facility or not. Okay, out of many subscribers, out of 250 subscribers. Then, if a subscriber uses that facility, the number of tasks sent by each active users has geometric distribution. So the first, each random variable, whether they're going to use or not, is a Bernoulli variable. Then, if that's successful, there's a geometric variable with a distribution parameter with 0.5, and therefore, so how many tasks a person is going to send is another random variable, and how long each task is going to take is another distribution. So there are 3 random variables that are in play here, okay? And the tasks are processed consecutively. So what is the probability? Imagine this is what happens in a day, 3 random variables. So it's a complicated problem. I have 250 users. So actually this is each user is like a Bernoulli variable, but the entire how many users are going to use the facility in a day is a binomial variable with n is equal to 250 and p is equal to 0.3. So the expected value of each person, how many so it's 75. So the expected value of users to use the facility in a day is 75. But it may be 70 in some day, it may be 80 in another day. This is a random variable. Each user sends a certain number of tasks with geometric distribution, and each task sent by each independent task, they take a different time. Okay, so it's a really complicated problem. And what we are asked is that, what is the probability that all the tasks will be processed in less than 24 hours? So is it going to, are these users going to flood over to the next day, or is the supercomputer has enough power to process all these tasks in a day? It will be finished. So what we are asked is that estimate the probability that the total time of these tasks is less than 24 hours with a margin of error 0.01 and with a confidence level 0.99. So here, when we do this, so what we do is our alpha is 0.01 here. Our confidence is 0.99, which means that our alpha is 0.01. The margin is also 0.01. So we z alpha over 2 becomes 2.5 divided by this and multiplied by 0.25. We also get the square of this. Before that, I just divided and directly multiplied. So after you find this 45,000, you have to take the square then. So it's going to be a really large number, but still in the order of millions. So it says 16,500. So this is how we use the Chebyshev's inequality to figure out this. And this 0.25 is the largest variance that we can have. And then the code that we write for this, as you can see, this is our size of Monte Carlo study. These are the parameters of the simulation. We have the the geometric, the gamma distribution and everything. So we fill in an array of n zeros total time it takes for each simulation. We are going to run, so we are going to simulate actually 16,000 days. It's not 16,000 users or 16,000 tasks. It's 16,577 days. We are going to, since we have the power, we can simulate that many days. Okay, so for each day, we first find randomly the total number of active users for that day. So we generate a Bernoulli number, we sum them up, that becomes our random numbers. For certain days, X is going to be 70, sometimes 77, sometimes 80, sometimes 85. That's a random variable, the number of active users. So for each number, for each active user, the number of tasks for each Y users is generated actually, I think, as an array. The total number of daily tasks for each task, we're going to generate a random variable that the time that it takes, and we compute the total time by adding up all those random variables we have generated, and at the end we have an array of n total time numbers, and we just say what is this total time is an array of 16,000 total times, and in how many of them we have, this is in seconds, I think, how many of them are less than 14, or maybe minutes, I don't know. Is it in minutes proportional? It should be minutes. This is the mean. So we just count how many of them were less than this, within this limit, and we take, you turned it first into zeros and ones, and if you take the average of those zeros and ones, this becomes your estimated probability. Okay, and this resulted estimated probability should be close to 0.17. It's a rather low probability, right? I mean, it's 0.7383 probability. The supercomputer will not have enough power to finish the entire number of tasks in one day. It will just finish in one day with 0.17 probability. And we do the same thing with means and standard deviations. First, let me quickly go over and how large this n should be. If we have a guess on what p can be, we can use p directly here. If not, we assume the worst, and we put here 1/4 here, which is 0.25. This is what we used. Okay. Usually, in most cases, because of our expectations, so we are never going to use the equations in this slide. Most probably, this one says that if they're not enough for binomial, if they're not large enough to use normal approximation, instead of referring to z alpha, if n is small, you can compute n without referring to z alpha, the normal distribution, if it's small. But most of the time, the n that is returned by this equation is on the order of thousands, so it will be enough for normal approximation to binomial. And for means and standard deviations, we do the same thing. Just like we estimated as a proportion, we get our sample, we take the average of our sample. For example, what is the average? If somebody asked, estimate the average total time of tasks in a day, what we would do is the total time here, instead of, if you just ignore this part, if you don't convert it to zeros and ones, if you take the mean total time, you would be estimating the mean time that is taken by these tasks for a day. Okay, and if you, for example, look at the sample standard deviation, you will be estimating the sample standard, you will be estimating the variance by looking at the sample standard deviation. So that's it. Let's, in the last 10 minutes, I'm going to quickly go, it's very similar to the example that we had, but we have a different function. So this assignment was given in 2017, and here it was the third assignment. Now it will be, your fourth assignment is going to be very similar to this one. So just like that example, we have multiple random variables. There's a single fisherman, but fisherman goes to catch some fish. The number of fish he can catch in an hour is a Poisson random variable with lambda is equal to 4. So we're going to simulate an hour of fishing. Now, the number of fish, so it's a Poisson with an expected value of 4. So sometimes he can catch 3 fish, 0 fish maybe, 2 fish, 8 fish. He'll catch different number of fish at 1 hour. The weight of each caught fish is a continuous random variable in kilograms with the following probability density function. So it's interesting. So the probability that the fish weighs less than 0 is 0, or the fish that he is going to catch in this lake are not larger than 3 kilograms. Okay, so it's below, it's between 0 and 3. So it may be 0 with certain probability, but it's going to be very small. It may be, you may catch very small fish with certain probability, but look at this PDF. It's a piecewise defined function. The probability that it's between 0 and 1 is this polynomial. The probability is it's between 1 and 2 is given by this PDF. So it's a piecewise defined PDF. It's difficult to maybe find its CDF, or maybe not that difficult, but still our goal is to conduct a Monte Carlo study to estimate the probability that the total weight of the fish he catches in 3 hours, not 1 hour. We are going to simulate 3 hours. So it's going to be a Poisson random variable with lambda is equal to 12. So if we are looking to have if you wonder what is if you define a random variable x as the number of fish he catches in 3 hours, that becomes a Poisson random variable with 3 lambda, which is 12. Okay, so we are going to have a random variable x with lambda is equal to 12. What we wonder is, can he catch fish with more than 25 kilograms in 3 hours? And we want 0.95 confidence, and we want to be within 0.005 of the actual probability. So this is our margin, this is our confidence. Use normal approximation to determine the size of your Monte Carlo simulation. So it says that use the formula that refers to that Z alpha, because the size is going to be large anyway. So what we need to do is we find Z alpha over 2 for Z 0.025. Since alpha is 0.05, let me write it here. What we're going to do is that 0.25 Z 0.025, which is alpha over 2, divided by our margin is 0.005. You're going to divide this by 0.005, take its square and multiply it with 0.5. So we can do that quickly. What was this Z? No, let me directly refer to this. Z 0.025. So 1.96. So 1.96 divided by, let's 1.96, which is a classical widely used number we use in our example. So we take this and we take its square, multiply it with the same thing, and multiply it with 0.25. That will be our size of our Monte Carlo study, which is 38,416. It has to be at least this. So to make sure, for example, if this is an exact number, but we can have, if you're, for example, if you conduct a Monte Carlo study, which is one larger than this, 38,417, it will be also okay. So it has to be at least this. So this is how we determine our Monte Carlo study. Then we are going to generate Poisson random variables, and then we are going to generate the weights for the number of fish that we catch. So how can we generate these weights? By using rejection sampling. Okay, so I'm going to show you the code. We are going to first we are asked the probability that is going to be larger than 25 kilograms. Also, we are going to estimate the total weight, and also we are going to estimate the standard deviation of the fish that we catch. Okay, so all these things are requested from us. So I will just quickly show you the code and then conclude that. So I'm going to share the PDF of this homework and this code with you on Autoclass. So let's see. So yeah, look at this. This is the same number we have found, 38,416. So this is our size of our Monte Carlo study. We have our lambda 12. And just similar to the code in the book, in that example, we have a total weight of 38,000 zeros. So this total weight the comment says it's a vector that keeps the total weight of the caught fish in 3 hours for each Monte Carlo run. You're going to simulate 3 hours of fishing 38,000 times. And yeah, this is our for loop. We first generate sample y, the number of caught fish in 3 hours using sampling from Poisson. Look at this code. This is familiar, right? This was the code to generate, to sample a Poisson variable. So there was a typo in the book, or a bug, in which this I is equal to I plus 1 was below this one. So this code here is to sample from a Poisson distribution with lambda is equal to 12. So y here, sorry, I here actually, if you're keeping track of count I, and we set it to y. Now y is the number of fish caught in this single simulation. It may be 12, it may be 11, it may be 10, it may be 18, okay? Now we're going to find the weight of each of these, for example, 13 fish. We set the weight to 0. Now sample y fish weights using rejection sampling. So in a for loop, we sample, and this is M0.7. 0.7 is something that you have to find by plotting that PDF. You can actually use MATLAB or other tools to plot these functions and find the maximum value attained in these polynomials. This will not be very difficult to do. You can even do it in Excel. And then this is the bound for x, our a and b. This is the c value, upper bound for y. So by using rejection sampling, again, this is our initial coordinates for rejection sampling, which we are going to ensure that it's going to be rejected. And initial value of f at cx is equal to 0 is 0.3 actually. We will start at 0.3 in our PDF. And in this while loop, we have our rejection sampling, and the thing, because it was given, so these are scaled cx and cy coordinates, because the PDF was given, actually also these these are not CDFs. This may be confusing. So these small f, it should be small f. These are PDF value that is evaluated, but yeah, it will give an error or so I use f also as the loop variable. I will have to change that. So let me undo this back to this. But since based on what x is, if x is between 0 and 1, I use this polynomial to evaluate the PDF. If x is between 1 and 2, I use this polynomial, which is the same polynomial that is given in this assignment. It's this one. If x is between 1 and 3, I use this polynomial to evaluate my PDF at cx. And based on that, I compare that with I evaluate my PDF, that becomes my f. I compare it with the cy value that was generated here. I compare it with that. If it's under the curve, I'm going to accept that as a sampled variable, and I'm going to increase my weight. So I will do this rejection sampling from this PDF for all the y fish one by one. And then the total weight in that day will be assigned to the weight I find here. And at the end, after all the simulations, 38,000 simulations are done, I turn my array into an array of zeros and ones. In how many of them the total number of kilograms was greater than 25? The mean of this 0, 1 array becomes my estimated proportion. The expected weight becomes the mean of this total weight, and the standard deviation of the weight becomes the sample standard deviation of this total weight array. This is an array of, it contains 38,000 weight values, each of them showing the weight of the fish caught in 3 hours. Okay, so it's this simple actually. After you have your ways to generate random numbers, all you need to do is find the size of a Monte Carlo study for a given confidence and given precision, and then you run simulations that many times, and at the end you will be surprised to figure out that what you find really is close to what, not really, but with high probability it will be close to what you're looking for. Okay, so as I said, I'm going to share you. Oh, how do we determine? I think it's like this. If you put 0 here for x, the initial value when x is equal to 0, in the first polynomial, when x is equal to 0, this polynomial is given. So if you plug in 0 here, as you can see, it gives you 0.3. It doesn't mean that the probability of catching 0 weight fish is 0.3. That's a point probability. But it means that the probability of catching very small weight fish is not that small. So there are many baby fish in that lake probably. So with 0.35 probability, maybe you will be catching, no, it's the initial CY. The initial CX is 0. Okay, so in this code, the initial CX, as you can see, is 0. The initial, so this is the CY is equal to M. So we again start our rejection sampling. So it's like this. Let me just quickly draw it here. Oh, not. Let me quickly draw it here. Let me get a new. So it tries to, yeah. Now, so here is how it looks like. Probably the function that we are having is something like this. For example, between 0 and 1, between 1 and 2, between 2 and 3. Okay, so this is, or maybe it was something like this. Maybe here it was high like this, which was like 0.7 here. That's our largest value. That's our M. Okay, and this 0.3 is where this PDF starts. So our initial point here is this. This becomes our initial point. So CX and CY actually is this point, 0 and 0.7, and this CY is the largest point here. And when you plug in CX into, which is 0, CX is 0 currently, this point you can see it has 0x coordinate, it has 0.7 y coordinate, the largest point. So if you plug in CX into F, you get 0.3. So that becomes your initial value. Yes, we calculate for 38,000 entries. We do this simulation for 38,000 times. So as you can see, the entire thing from the beginning, how many fish there is going to be, is done 38,000 times. So this total weight is a 38,000 size array, and in this, our overall loop is 38,000, runs 38,000 times, and for each one, we generate first a Poisson number, and inside that we have a loop to generate the weight for each caught fish, and the fish that is going to be caught are going to be a CX-CY value, which is under the accepted sample using rejection sample will be a point which is under that piecewise PDF, piecewise curve that I showed here. So this 0. The PDF was something like this. It's interesting, right? It's very strange that for the below 0, the probability is 0, but the PDF starts at exactly 0.3. So it's a PDF that is like this. It's a strange PDF, but that's how it is. And this was why the initial value of the FCX is 0.3. We could actually have evaluated that in this code. We directly write 0.3 here, but we could have directly have written this. I mean, if I write here, oops, if I copy it here, okay, you will see that it's going to be the same thing as setting it to 0.3 because CX here is 0, 0 times 0 times 0.3. So it's having this and evaluating it there. And this is as long as the generated random CY values are above the curve, we keep rejecting them. The first F for a CX that is under the curve, we accept that CX as the weight of the fish that is sampled from this arbitrary distribution. So this thing here inside this for loop is for generating the weight of a single fish, and it is inside our outer for loop, which shows that it's for y number of fish, and that's how we keep accumulating fish weights for each y fish, and that becomes our total weight. Actually, you can use I think you will be using MATLAB. The code, if you look at the code, it doesn't look very much different than C or Python or Java. It's just an imperative programming language here. And since in MATLAB, many of these functions like gamma function or other functions are readily available, like taking the mean. And this part is really easy. You don't need to have a for loop. So you will be using MATLAB. So you will be your code for homework 4 is going to look very similar to this one. Okay, what you will be doing, this 40 lines of code, what you will be doing is going to be very similar to this one. You will have some rejection sampling. You will sample something from either lambda, gamma, exponential, whatever the homework text is going to say, but it will be very similar to that. So you will be using MATLAB. Any other questions? And this concludes our discussion on chapter 5. You may try to run this and see what the probability of fish code is. You may, if you wonder what the average weight of fish code by this person, try to run this code that I'm going to put on OptiClass on week 13. On week 13, material and section, all sections, week 13, I'm going to put both the PDF of this and this code, so you can try and run it on MATLAB and see what the computed probabilities are going to look like. One thing that can be in Octave Online is that it may take more than 15 seconds to perform this many simulations. So you should keep hitting the enter button to request more time from Octave Online, or you may install MATLAB, which I think our university has a license for MATLAB, and try to run this on MATLAB, the same code with no time restriction. But even in Octave Online, it's possible. I think it finishes maybe in at most 2 minutes or so. These simulations, you'll be able to run in around 2 minutes, and you will see the answer after 2 minutes. All right, let me stop recording now.